And now I want to welcome Łukasz Langa, our CPython developer in residence and our first keynote speaker. Let's give him a warm welcome.
Hi there. This is easily the biggest crowd I've ever spoken to, so I'm a little nervous. My name is Łukasz. I come from the internet. You can find me in all sorts of places online, but I've been coming to PyCon for a while now, and I'll be here for the entire event, so I'm happy to answer any questions you might have about any subject. I like Python, so we can talk about Python. I also like Robert Maynard Persig's Zen and the Art of Motorcycle Maintenance. That's a pictogram from the cover of the book. First read it some 10 years ago, and it massively influenced me. It's like some meditation about technology that also is connecting it to how people perceive art. It talks a lot about quality, and it never really left me since. I just reread it this month, and it totally holds up. So highly recommend you looking it up if you haven't read it yet. And in fact, we're going to be talking about quality here too, but it's going to be maybe a little bit of a mundane kind of quality, because we're going to be talking about type annotations. Type annotations are here to stay. They've been first added to Python 3.5, and ever since there's been a number of PEPs that made them easier to use and made them more powerful to express more complex and complex types. So if you haven't ever annotated any application yet, you're likely to be, in for a treat soon. And if you did, you might have some experiences with it. Some of us have been annotating Python programs for quite a while now. And with this experience, we have kind of devised some best practices on how to do this, how to write code so that it doesn't really fight the type checker. And this is what we're going to be talking about today. And also about some what we consider anti-patterns, where what you're trying to do works against what the type checker will want from you. And finally, we'll cover some limitations of static typing compared to what the runtime Python allows you to do, and whether they're a ball and chain or more of something that you should be really kind of grateful to have. So why do we even have type annotations in the first place? Looking at this very simple code example that pretty much reads like English, we can see that it's a process all function accepting one argument, which is items, and for each of those items, it will find a children attribute on them and call a process method. Easy. But even in such a small example, there might be a lot of complexity and questions hiding. In this particular case, what is items? We don't really know. Like in Python, items, maybe there were pairs in dictionaries, right? Key value pairs. But here we know that this is not the case because those don't have a children attribute, so it's something else. How do we find out? If there's no docstring, we need to grep through our code base to find out. But finding items in a big code base, not very easy. So how about looking for the children attribute? Again, not very easy. How about we grep for a process method? In all likelihood, you're going to have more than one. So you need some form of documentation. And you need it if you're using powerful features of Python like its dynamicism as well, because in this case, we have some proxy that has instances which are callable, just like functions. And from the signature here, you see that you can call it with any arguments. Anything goes. It's all good. But is it? Experience shows that there is only one, or a few cases where it makes sense to call this proxy with some set of arguments. So what are they? Well, either we need to read the body of the function, or we're lucky enough to have some documentation which is either in a docstring or provided in some Sphinx docs on the side. But I would argue that type annotations are a wonderful form of documentation which works for you because it will both allow people onboarded to a new code base to be productive quicker, but it also will allow you yourself to remember what you thought about the function you were writing 6 months or 6 years back. It helps with review, it helps with debugging, but also it's machine readable. Thanks to a type checker, we can validate assumptions about code that you're writing right now and keep validating those assumptions into the future. So if you change a function, which is very likely to happen, we modify our software, we keep maintaining it, the type checker might still be checking whether the API stays sane. So I could finish right now and we could just go to the coffee break sooner because I hope I convinced you it's all good. But what if your type annotations look something more like this? This is a screenshot taken by Ned Batchelder and posted on Twitter last year by him. He said, you know, I'm looking through this PyTest documentation and like, what is this? Is this the future? Are we supposed to be able to read this? Like, my response at the time was like, yeah, no. Like, obviously, even the biggest fan of typing will tell you that this is not optimal. This is not what we want. Fortunately, there is plenty of ways in which, even without bothering PyTest developers, we can improve the situation. So we can make this more readable. So I responded on that Twitter thread, but people started piling on with their own favorite examples. We're like, how about this example? How about this example? How about this? And I came to the conclusion that sometimes ugly type annotations hint at ugly code. You know, it's a controversial thing to say, maybe insolent, but if you're not at least a little bit controversial doing a keynote, then how are you living your life, you know? Like, it needs to be memorable, but also I'm pretty serious. Like, type annotations don't create additional complexity. They expose complexity that was always there. And hold on. I understand that 8-year-olds who first dabble with programming thanks to Python don't necessarily need to know all this, and it's wonderful that Python allows that. I understand we have, even in the audience, plenty of professionals who wouldn't otherwise call themselves programmers, but they're enabled by Python to be productive in their respective fields. So I understand all this. However, with experience, you're going to be handling increasing amounts of complexity. Your 5-line long snippets will become 50-line long scripts and then 500 lines long. And soon enough, you're going to be looking at 500,000 lines of code that you're maintaining. And with that increased complexity, your understanding of what's going on has to increase as well. Otherwise, you're going to end up with a big ball of mud that is not really maintainable, and its behavior cannot be really easily reasoned about. So let's talk about how we can structure our code such that it actually makes type annotations less ugly. First, let's actually solve this case that Ned Batchelder showed us because it's particularly egregious. And luckily, we can do this with only a few simple things. First of all, please use modern typing syntax. We are working on Python 3.11 right now. Python 3.10 was released in October, and Python 3.9 will see its final bug fix release just 2 weeks from now. What that means is there is little excuse not using Python 3.9 right now. It's unstable Debian. Come on. So using modern typing syntax in Python 3.9 allows you to use built-in types as generic collections, which is tremendously useful. And in Python 3.10, you can use the pipe operator for unions, which combined make for really terse but readable syntax that expresses even pretty complex types. Let's see an example. We have a match argument to some function, which can be either a string or a regular expression pattern or a none. This is how you express it. And the only piece of complexity here is that it's a regular expression of string, because it could be a regular expression of bytes. So I hope that even if this is the first time you're seeing type annotations in this form, you can kind of see why it's read like this. But after a while, it becomes second nature. Just looking at those types, you know what they are. Let's look at a more complex example where we don't want an object of a type. We want to be passed a class. So in this case, we would say we expect some type to be given to us. Type of E, not E itself, not an instance of an object, a class. Or we want many of those classes in a tuple. So we either accept a type of E or a tuple of many of those types. And with those two examples combined, we end up with a much more readable piece of documentation that is an equivalent of what we've seen before. We can really read what it does right now, which is a context manager that responds to a raised exception, and you need to specify what you expect to be raised, either one type of an exception or multiple in a tuple. And you can optionally say that we should be matching some piece of message in this context manager. So it's either a string or a pattern of a string. If we don't specify anything, the default value is none. Done, okay, we understand what is going on right now. The context manager actually returns a raised context that is dependent on the type of the exception that we gave it. Okay, so cool. But I kind of, helped it be more readable by changing formatting here a bit. And it's maybe a mundane thing to say right now, but I do believe that standardizing signature formatting has a lot of impact on how readable annotations later are, because some pre-existing conventions on how to format them don't really gel well with annotations, especially the ones that try to hang subsequent arguments under the opening parenthesis. It ends up looking something like this. It's very small. I don't expect you to be able to read what is there. I don't even expect you to be able to say how many arguments this function accepts. It's not very nice, and there's little space for the return annotation as well. So how do you fix it? Well, I have one simple suggestion. Just blacken that shit, Like, it'll do it for you. It'll do it automatically. This will allow you to increase the font size over twice. Now we can actually see what's going on. We can see the name of the function and that it accepts 3 arguments. Cool, and there's plenty of space for the return annotation, which is a dictionary of strings to a set of strings. But I'm not particularly happy about this annotation, because what are those strings? Remember, type annotations are human readable documentation. They're meant for humans first. So my suggestion to you is to give those types meaningful names. It doesn't matter to the type checker, and it matters even less to runtime Python, which doesn't do much with type annotations. But it matters a lot to a human. Let's see an example. If we have a show lyrics function that takes some query list of string and takes some lyrics database, which is a dictionary of string, to another dictionary of string to string, this is everything that a type checker needs. But I don't quite understand what is going on here. So let us help ourselves by giving names to all those strings. For example, looking at the inner dictionary, we can say that the keys are song names and the values are lyrics. Now the mystery of the inner dictionary is solved, so we can even give that entire dictionary a name, song to lyrics, and the annotation magically becomes less verbose. And we can do this with the external dictionary too, saying the keys here are actually artist names. So now, with all of those annotations, we have a much shorter function signature, and also we can reuse those human readable names in other functions. You can expect that if we are being passed a lyrics database in one function, there must be some other function that produces it, right? And there might be others that filter them, mutate them, or whatnot. So reusing the same annotations that communicate to humans what those things are, tremendously useful, highly recommended. So now we are moving from, visual things, from simple modifications, to more of like code refactoring area. So we're going to be making increasing changes to this, but this is all still about human understanding of the code at hand. So for example, I would argue that you should be making your functions small and simple, and to dispatch early to specialize. Detractors of typing love to give you examples where they would use some super dynamic function found in Python, say the max built-in, and they will say, hey, try to type that and see what happens. Well, of course, this isn't even a built-in that has one signature. It's got 2. And those are plenty dynamic here as well. And they allow for some funky stuff, like the iterable in the first form, doesn't have to have the same types as the optional default value. And the arguments given in the second form might be of incompatible types too. Like, it's all good. You can all do this, and it will work magically in Python. And are you using functions like these? Of course you are. This is the core of Python, the vocabulary that we have that doesn't matter what kinds of data you're putting in, the same verbs apply. So it's wonderful to have this in Python. But when was the last time you actually constructed a function that was this dynamic? I would argue that if you're raising your hand right now, which I can't really see, like you're an author of some library or framework that needs this sort of dynamicism, and Godspeed to you. Yes, in this case, static typing will be a little verbose, but for everybody else, for end user code, it's very unlikely for you to have to deal with this sort of dynamicism. So let's just put things in perspective. Well, if you do, then you will look inside the implementation of a function like this, because the documentation doesn't tell you that if you're implementing something that is tremendously dynamic, the implementation tends to look sort of like this. There's some dispatch there, there's 20 lines here dealing with one form and 10 lines there dealing with another form. It's not the kind of function that you love to read. It's hard to test it thoroughly. Right now, you can talk about cyclomatic complexity, whether you covered actually all paths that are possible. The max built-in is wonderful, but Python is powerful also due to its maturity. Like all the edge cases were already ironed out. You can pretty much use it without fear that some edge case was not covered. With functions that you're writing yourself, how likely is it that there is going to be some edge case that slips in? Well, there might be a case like that. So I would recommend you dispatch early. Replace the implementations with smaller functions that only respond to a subset of what's going on. This allows usually for shorter function signatures of those sub-functions, let's call them that. The external one will still have a horrible, big function signature with long type annotations, but it is what it is. Life looks like that. But splitting the function into many sub-functions allow us to now see the bird's eye view of what's going on. And for example, to identify the bug that was on the screen all along, which is that we accept a Boolean as the function signature tells us, but Booleans happen to be integers, so maybe we don't actually want to parse it as an integer, which we are here because this is the ordering in which the ifs and elifs go. So by splitting the functions, it's more likely for you during testing to identify this problem. And you can assert maybe that parseInt does not want to get Booleans because they're not exactly what we want to deal with. And if you look at the function signature of the subfunction, it becomes pretty much trivial. One argument, which is only an int, we return an item. Done. Right. But I don't want you to only write trivial functions like this. Like, this is no way to live. And the robustness principle tells us that we should be flexible in what we accept and strict with what we emit. When we're talking about functions, that first part applies to the arguments of the function, and the other applies to what we return from the function. Let me give you an example from the black code base. We're looking for configuration. So we have a bunch of candidates for paths where configuration might hide, and then we're going to be returning a path to a configuration file if we find it, or none if we don't. Well, do we need this argument to be a tuple? Maybe it's not really that important for it to be exactly a tuple. All we're doing here is iterating over it. So maybe saying, just give me an iterable is a better idea, because now the caller of this function is able to provide you a list that they already produced. So they don't have to convert anything. They can just pass this data right there. Maybe they have a set, and maybe that's also fine. So this is what we mean about being flexible in what we accept. But we're strict in what we emit. And are we here? Not really, because we either give you a path or give you none. And this is not perfect, because it forces the caller of the function to always check. What is it that they received? Is it none? Sometimes people will forget to check. Sometimes they will just pass this responsibility on to further functions, making none proliferate in your code base, which isn't something that you particularly want. So how do you solve this? Well, you can, in fact, use exceptions for exceptional states. It's what Python wants you to do. In this particular case, you can use a lookup error, one of my favorite built-in exception types. Index error and key error both inherit from it, but it's also useful for a wide array of cases like this, where we're finding something and failing. So yes, you should be using exceptions for exceptional states, but there's another thing that you can do without having to modify types there. So you can use empty values. This is especially natural when you're dealing with collections. For example, if you have a function that lists all the users that are currently logged into our application, it's perfectly reasonable to return an empty list if no user happens to be logged in to your application at this point. But this makes also sense, depending on context, to do for scalars. So Python does allow for falsy values when we're talking about numbers, and it allows for falsy values with booleans and empty strings and so on. Sometimes that's dangerous, so what you want is actually an exception to inform the caller that, you know, we actually failed to find something and the default value would hide this fact. But if you ever used a default dict, you know that there's plenty of cases where an empty value makes perfect sense. None is a particular special example where returning it from a function is annoying, but it's not the only one. In fact, any kind of type union that you're returning from your function is going to be hurting your users because they will be forced to check which one did I get. And if they do this and they write some if-elif chain and you later change your function, we already talked about booleans being ints, but this only stands in any form of subclassing. Code that looks like it works might not actually do what you want. So I always recommend avoiding returning unions from functions as much as you can help it. So coming back to this robustness principle, when we say that we want to be flexible in what we accept and strict in what we return, what we're really saying is that we want to be vague in what we accept and concrete in what we return. What I mean by this is that in the arguments here, we accept a collection. We don't really care what it is. You might give me a set, you might give me a dictionary, you might give me whatever else. We only need a collection. But when we are returning a list of items, we should say that to the user, not an iterable, not a sequence. Let's tell them what they received. By telling them exactly what they're getting, they can now utilize append methods, they can rely on the order of the things that they got, and so on and so on. So that's pretty much the robustness principle in hindsight, right? Like in, I don't know, like high level. But sometimes it's not really that easy to be, you know, truthful to the dot. Typing might make it overly verbose, or it might actually be not helpful because you're going to be spending a lot of time only to end up with something that's more brittle than what you wanted. Let me give you two examples of this. So the first example is another piece of code from Black where we split a single line into many lines, and we're generating it because we're efficient. So we're yielding those lines. What that is a generator. That generator generates lines. It does not accept anything being sent to it, so none. And it does not emit anything on stop iteration, so another none. But I'm not really super happy with this annotation because it is super verbose. So instead what I end up using is to say I'm returning an iterator of line. Is that more vague? Yes, a little. But what can you do with a generator that does not accept anything being sent to it and it doesn't do anything special on stop iteration? Well, you can pretty much only iterate over it. So it's pretty truthful to what you're wanting. And it's also a much simpler annotation to be reading. The opposite example would be in arguments, where you're accepting a file argument, an open file. But you're looking at the body of your function and you're like, I'm not really using the entire API of file. I'm only using this small slice. So maybe any file-like object will be great, you know? And how do you annotate that? Well, either you look at your application and see what are the possibilities of types that I could put there. And there's going to be some big union of those types. Or you can use structural typing, so protocols, and actually define what methods and attributes you want people to be to have to implement to conform to your file-like object. Or you can just say any, which is essentially shutting the type checker up, saying, you know, I'm going to be doing weird things here. Please don't raise type errors. So you can do those three things. And I used to be in the camp that actually specified everything to the dot so that, you know, we sliced the contract as thinly as possible. But I grew to stop doing that. Now when I need a file, I'll tell you exactly that. Please just give me IO of text and we're good. Why? Because of my previous experiences as a beginner core developer back in 2010, I was making config parser a little better. And I deprecated a function that had multiple issues with it, with a better function, of course, read file. And I didn't want to have any duplication of the implementation. So I remade the readfp deprecated function to actually use the new one internally. The argument we accept here, fp, is an open file. So it wasn't really a problem to me that before we were calling readline on this open file, but now we were iterating over that new, in that new implementation. So obviously it wasn't a problem for me, but it was for other people who were passing file-like objects to this function, and that stopped working. So I had to put this piece of documentation that is still there now to shame me forever, that I haven't really foreseen this problem. But, you know, and if you have to rationalize your mistakes later in life, because, you know, otherwise you're going to just be a sad, sad person with plenty of regret. So I turned to realize that, you know, maybe when I wanted a file and the documentation never said anything else, that please give me an open file, me changing my requirements as to which part of that file I want to use isn't really that unreasonable. So if you spend your time cutting your contract really neatly to expose only the minimum of what you want, that's perfect, that's great. But in the future, you might actually want a little more. For example, if your function accepts a file-like object, but later on you realize that you want to log an error case and actually tell people the path to, you know, where stuff gets wrong, now you have to use the .name attribute on a file-like object, and you might have not required this before. This is not awesome because existing code, especially on PyPI, if this is open source, might give you a lot of grief. So in the end, I tend to simplify and just, you know, be concrete about the types that I expect people to be able to put, even if something more will be, in fact, accepted at runtime. I want to be concrete because it's my contract from me to you, from programmer to a programmer. So now let's talk about the mismatch between static typing and what Python allows to do at runtime, because it allows for a lot. So you can perceive some of the limitations of static typing as like seatbelts. You just put them on, you don't even, you know, think about it. Or you might think about those limitations more like the masks that you're wearing. You know, a sad, sad reality that we're in, but you know, you'd rather not. So let's see. Let's start with a simple thing. One variable, one type. Python will not complain if you reassign a given name to mean something entirely different, to have a different type, to have a totally incompatible value later on. It's all good, you know, in terms of how runtime perceives this. A type checker will be annoyed at you if you do this. So now the question is, who's right? Well, obviously, Python at runtime is right. It will run your code, fine. But do you need this form of dynamicism all the time? If you even have a very simple example, that is a little jarring because your function signature tells you that argument is one thing, whereas after this conversion to datetime, it is suddenly something else. No great. especially when this conversion doesn't happen right there on line 1, but happens on line 20 of this function, or it happens only in some conditional, or better yet, if this is in an object and under init creates a bunch of attributes of one type, but then some other method modifies them to mean something else. It is very confusing very quickly, and it's hard to say whether this was the intent of the programmer. So static typing errs on the side of caution, saying, you know, this used to be a string and now you're trying to make it a datetime. Are you sure? The solution here is obvious and we should just move on, just use another name, right? Like, I know that there's implementers of Python interpreters in the room, so they will say, hey, but like, they're not exactly free. But for our intent and purpose here, they pretty much are. Like, just adding just one more name is not going to destroy the world. In fact, it's useful, because if you ever debug this function and you list its locals, now you will be able to see the value pre-conversion and post-conversion. So if the bug is actually in the convert to datetime function, it will be easier for you to identify this, faster for you to identify this. This all comes down to the difference between doc typing, so structural typing, and nominal typing, so us telling that this is an int, this is a string, this is a list of string. This difference is highlighted sometimes, you know, when people talk about type annotations, but for me personally, they aren't actually that different. So it is true entirely that when we are running Python code, unless you're running is instance or is subclass, Python doesn't care about the types. All it cares about is if you have an object and you look up some attribute on it, that it finds this attribute. Or if you're calling a method on an object, it finds that method and its signature is compatible with whatever arguments were given during the call. As long as that's fine, it doesn't care, right? If it quacks like a duck, it's a duck, like as much as we care. Nominal subtyping means that in function signatures, in type annotations, we don't really specify what we're going to be using. We're saying what this thing should be, what it is. So we need an integer, we need a decimal, we need a string, we need a path object, this sort of thing. But if you look at a program, even at a big one, there's always only a finite set of which objects actually conform to the operations that you're doing on the object within your function. So at worst, what you will be dealing with is some union of possible types that can actually successfully respond to whatever the function is doing with a given argument. So with that in mind, nominally listing those, either one in the happy case or a union of a few, isn't really that bad. There is not really a huge disconnect there. And better yet, nominal typing doesn't mean you only have to specify concrete classes. There's abstract base classes now, so you can say iterable of string just as well if you don't mean a particular implementation, only care about some structure. And if you really want flexible structure, protocols allow for that too. But giving nominal types is sometimes helpful for us. For example, when we're dealing with dynamicism of Python that can be sometimes dangerous. For example, in Python, a string is also an iterable of strings. If you pass a single string to a for loop, it will happily split the string character per character and do the iteration with no complaints. But if we look at the previous example, in the actual black code, what we have is not an iterable of path, which is a happy case, but an iterable of string, where a single string is also one. So do we want this? Is this a feature for us? If we by mistake specify a single string, now the for loop will cut the string into characters and happily try them as candidates. This is meaningless. So what we have to do is either to do this dreaded is instance where duck type people will tell you, don't use this instance, like that's anti-duck typing. But you have to do it here, because otherwise you will be opening yourself up to this bug. What you can also do, though, is to just say, we don't want iterable of string. We want a list of string. Yes, other types will be accepted too, but through this simplification, we are dealing with a class of errors that people can do. And this lets us to typing things that are not quite clear to how to do. very often you'll be tempted to just put any there. So let's talk about this for a second. People who are just beginning with typing often ask me like, you know, isn't object the base class of everything in Python? So why do we need to import any from typing? Like if I say this should be object, like won't it be true as well? Well, for the typing use case, they're actually opposites. When you are typing an argument to be a string, what it tells the type checker is that any operation which is valid on a string, so concatenating it to another string or calling the upper method, all those things are fine. But if you call, say, append, the type checker will now complain because that operation is not implemented on strings. So if you would say object, right, if you would annotate an argument as object, what that tells the type checker is that any operation that is valid on the base object type is accepted and nothing else. What operations do objects accept? Well, you can check its ID, you can convert it to a Boolean, you can see its wrapper. Not much than that, right? All the upper appends and other attributes are not there on the base type. So any is the opposite. It tells the type checker that whatever operation the user will do inside that function should be considered valid. Please don't raise exceptions there. So any is tempting. You might be tempted to use it whenever you don't know what you should be putting instead. But it's not that great. And the reason why it's not is it will, again, proliferate just like none does and silence actually valid warnings from the type checker because now it is instructed by you explicitly to ignore problems that it sees elsewhere in your code. So any should be sort of taken with a grain of salt and used with care. And let me just finish with another controversial thing, because you know, like I only had one so far, which is that I started considering strings to be not much better than any, because a string can be an identifier from a database, it can be an email address, it can be an entire poem or a JSON encoded image, it can be whatever. So when you use strings as types everywhere, what are you getting? You don't actually know. So I'm not saying you should be not using strings from now on, but whenever you're seeing that your function accepts a bunch of strings everywhere, let's think about like, hey, maybe there is some other representation that I can use that will explain my intent better and will make sure that I'm not swapping a string that is incompatible with one that I actually wanted. So I could still keep talking and keep you from the nice coffee break that will come after. But there's only that much of typing information a person can reasonably get at one point. So let me just give you some further reading. If you're actually dealing with JSON that I just mentioned, typedict will allow you to say that if the key is named email, it's going to be a string. But if it's named birth year, it's going to be a number. Right? So you can actually now annotate strongly some random dictionaries you're getting from the internet. We already talked about giving meaningful names to strings, but there's still nothing stopping you from putting an artist name where a song name should go. So new type is a functionality of typing where you can actually semantically differentiate between two kinds of strings or numbers or whatever else. So look up new type, it is very good for that. And finally, in the talk, you might have gotten the impression that I'm not really that happy about, structural typing, about duck type. No, it's not what I'm saying. It's just that, sometimes it is a little too heavy of a tool for what you actually need. But since my name is on the PEP, please read the protocols PEP. It's a wonderful feature of typing as well, which gives us a lot of flexibility to actually merge duck typing with type checkers. So go ahead and look. It'll likely solve issues that you might be having later on in the future. And a class of errors that, and like annotations that I like to talk about, but there's no time right now, is self-types. So whenever a function accepts some object and returns another one like it, or accepts a type and returns an instance of it. This is a very, very popular scheme in Python because it's how methods and class methods work. So reading on self-type and how to use type vars and then newly added self is going to help you actually navigate this sort of thing, especially when subclassing is involved. And finally, variance is a word where I'm like, sure to lose the audience. So instead of talking about it right now, I'm going to be giving a lightning talk later today, just in 5 minutes, just about variance. Like, you might just laugh at it later, but you might actually get what contravariance, covariance, and invariance are. And the funny thing about this is that people hate static typing for variance. They're like, those weird terms, like, why are you imposing this on me? But this is something that you're dealing with in collections, even if you don't think about this. Same with list of substitution principle. You might be breaking it even if you've never used a type checker. The type checker only exposes those classes of issues. So reading up on all of this is very, very useful. So, there can be too much of a good thing, just like with this talk. So for example, if you find yourself, fighting type annotations, if you find yourself unable to express what is happening, you can take a step back and ask yourself, hey, like, Python is dynamic. Should I be using those features? Yes, of course. Like, this is why we're on PyCon, come on. Like, dynamicism is great. The flexibility that we have from runtime introspection is wonderful. We should be using those things. But should you be 100% dynamic 100% of the time? I would argue that you don't have to. So whenever you find that your types are especially ugly, just consider refactoring. Maybe you can simplify. And if you cannot, maybe you can shove the complexity somewhere else. So divide and conquer. This doesn't fundamentally change the amount of complexity in the system, but it will let you deal with a smaller amount at a time, which even in Zen of Python is a good thing. So with that in mind, I'm not sure if we have time for questions right now. If we do, that's great. If not, I'm happy to answer any questions you might be having if you find me at the conference. I'm going to be masked, so it's going to be a challenge for you, but I'm here for you. Thank you for your attention.